Hi, thanks for joining me. Today I'm going to be going over problem 3 from week 5 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details of the competition. Anyway, this is the problem I'm going to be tackling today. Let P1, P2 all the way up to Pn denote points on the plane. We want to show that for some I, the set of distances between Pi and the other points contains at least the square root of n minus 3/4 minus a half elements. So another way of kind of rephrasing this problem is we have our n points on the plane, say one there, one there, one there, one there, I don't know, something like that. Suppose n is 4, we only have 4 points. Then what we were going to do is look at each of the points here. So let's start with this point here, and we'll look at the set of distances of the other points from that point. So say this point here is 1 unit away, and let's say this one here is 2 units away, and this one here is also 1 unit away, suppose. Then there are only 2 different numbers there, so we'd kind of assign a score of 2 to that point. And then we do this for all the other points as well, and what we want to do is show that there's at least one vertex with a score of at least this guy here. So I hope that all makes sense. If you want to have a go at the problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the way we're going to solve this problem is by using the score notation I kind of mentioned at the end. So for each of these points we're going to assign a score, and the score of each point is going to be the number of different distances of the other points from that point. And of course, if we define m to be the maximum of these scores, so the maximum of score P1, the score of P2, and so on, all the way up to the score of Pn, our problem is to show that m is at least the square root of n minus 3/4 minus a half. Now the way we're going to show that, or the way we're going to derive that inequality, is firstly by just choosing the leftmost point. So in this kind of example setup, that's going to be this point here, and we're going to call that point PL for now. Then the first thing we're going to do is we're going to assign the score of PL, and we're just going to denote that with S. So S is just going to be the score of PL. So that's the number of different distances from PL. And I deliberately kind of drawn this example to make everything make a little bit of sense. But anyway, let's suppose that this point here is 1 unit away from PL. So it's going to be a distance 1 from PL. These guys here, suppose, are 2 units from PL. And let's suppose that one there is 3 units. This one here is 4 units. This one here is 5 units, and this one here is 6 units. Now I guess perhaps it's not the best idea to be using integers for each of these, because all of these numbers here could be, you know, decimals or irrationals or whatever we want. But yeah, they don't have to be integers, but just to keep everything nice and easy to follow, I made everything an integer. Anyway, these are kind of the set of distances from PL, so the score will be 6, because there are 6 different distances from PL. Namely, there's at least one point with 1 unit distance, one with 2 unit, one with 3, one with 4, one with 5, and one with 6. So the score of PL in this case, I'll perhaps put in inverted commas, is 6. Just so we know that that's only in this case, but S is what we'd have in general. The next thing we want to do is define T. And T is going to be kind of the maximum number of points which are equidistant from PL. So max number of points equidistant from PL, like so. So what do I mean by this? Well, in this setup here, the answer to that will be 5. The number of points is 5, because clearly we can see that there are 5 points which are exactly 2 units away from PL. So all those 5 points are equidistant from PL, and there's no other set of points larger than 5, all of which are equidistant from PL. So in this case, T would be equal to 5, like so. Now what we want to do is notice that ST must be bigger than or equal to n minus 1. Now why is this true? Well, if we have a look at how we define T, it's the maximum number of points equidistant from PL. So if we, you know, for all of these distances here, 1, 2, 3, 4, 5, 6, if we kind of group the ones which are equidistant together, and we'll get a bunch of sets. In this case, we get S many sets, because we'll have S different distances. Then we know that each of those distances must be at most T, because each of them, by definition of T, because T is the maximum number of points in essentially each of these sets. But how many kind of points are there in total in all of the sets? Well, it's n minus 1. So we must have the s times t, in other words, the cardinality of all these sets must be at least n minus 1, because we know t is the maximum number of points in each set, and the number of sets is just s. So s times t must be at most the number of elements in the set, which is, or in elements in all the sets, which is n minus 1. So we get s times t is at least n minus 1. But also, if we have a look at m, we also must have that m is clearly going to be bigger than s, because s is the score of PL, and clearly just from this thing here, we must have that m is bigger than or equal to all of these guys here. So in particular, it's bigger than or equal to the score of PL, so m is bigger than or equal to s, but also we get that m is bigger than or equal to t minus 1. Now why is that true? Well, if we look at, say, one of these points, so we look at what t is, so it's the maximum number of points equidistant from PL, so we're going to find one of these points. So in this case, it's going to be one of these points on which are 2 units away, and let's just choose this one here. And I guess one thing to notice is, because these are equidistant, these kind of form a circle. Okay, that's the circle's supposed to pass through all those points, but it forms kind of a circle around the point PL, where PL is the center and all of these points fall on it. But then if we just take a point on this circle, so this guy here, we know that each of these guys here are going to be a different distance from this guy here. So like this guy here is clearly going to have a shorter distance to travel if it wants to get to here than this guy will, and so on for all the other points. They're all going to be a different number of distances from this guy here. Well, how many distances are there? Well, there's going to be t minus 1. Okay, so we get that m is bigger than or equal to t minus 1. So we've got these three inequalities here. Let me clean up the whiteboard, and I'll show that m must be bigger than or equal to the square root of n minus 3/4 minus a half. Okay, so we just derived these three inequalities here, and the first thing we're going to do is just add 1 to both sides of this inequality. So we get m plus 1 is bigger than or equal to t, we have that m is bigger than or equal to s, and we also have that st is bigger than or equal to n minus 1. Now if you just have a stare at these, hopefully the kind of intuitive thing to do is multiply these two inequalities together, so we're going to get an st. But before we do that, let's just notice that everything we're working with here is non-negative, so we don't ever have to worry about signs, the inequalities changing sign or anything like that. So if we do this inequality times this inequality, we're going to get an m times m plus 1 is bigger than or equal to st. But from this inequality here, we obviously know that st is bigger than or equal to n minus 1. So let's cut out the middleman, and we get that m times m plus 1 is bigger than or equal to n minus 1. But this left-hand side here, if we just expand it out, is just m squared plus m. And then if I just add a quarter to both sides, you can perhaps guess what I'm going to do. This thing here is going to turn into n minus 3/4. But then this thing here is kind of a perfect square. This is just m plus a half all squared. So get m plus a half all squared is bigger than or equal to n minus 3/4, like so. And then notice again that because m plus a half is a non-negative number and n minus 3/4 is non-negative, because n, remember, is a positive number, I can take the square roots of both sides, and this won't change anything. So if I take square roots of both sides, I get m plus a half is bigger than or equal to the square root of n minus 3/4. And then of course just subtracting a half from both sides gives us that m is bigger than or equal to the square root of n minus 3/4 minus a half. And that's exactly what we wanted to prove. I hope that has all made sense, and I hope you've managed to follow along. Thank you for watching. I'll catch you in the next one. Have a great day.